You cut the soda, you skipped the dessert. You started reading labels for grams of added sugar the way people once read labels for grams of fat, and every source of health advice you encountered agreed with the decision. Less sugar, lower inflammation, better numbers at your next physical. Nobody mentioned the brain sitting inside your skull, the organ that runs almost entirely on the very molecule you just started removing from your plate. Your brain weighs about 2% of your total body weight. At rest, it burns roughly 20% of your body's entire energy budget, a ratio documented by Marcus Raichle and Deborah Gusnard at Washington University in a 2002 paper in the Proceedings of the National Academy of Sciences. 2% of the mass, 1/5 of the fuel. No other organ comes close to that ratio, and the reason is electrical, not metabolic in the way people usually picture metabolism. Every signal a neuron sends is a voltage event. Sodium and potassium ions move across a membrane, a pump spends ATP to restore the gradient afterward, and the cycle repeats billions of times a second, across roughly 86 billion neurons. The ATP for that pump comes almost entirely from glucose, not protein, not the fat sitting on your body, glucose specifically, because for most of your life your neurons run on one dominant substrate, and the delivery system for that substrate is a single class of transporter protein called GLUT1. GLUT1 sits in the wall of every capillary lining your blood-brain barrier, ferrying glucose molecules out of the blood and into the tissue that will burn them. There is a rare genetic condition, first described by pediatric neurologist Darryl DeVivo in 1991, and now called GLUT1 deficiency syndrome, where a child is born with too few of these transporters. Blood glucose in these children is often completely normal. The sugar is right there in the bloodstream. It simply cannot cross into the brain fast enough, and the result is seizures, developmental delay, and a movement disorder that worsens with fasting and improves with a ketogenic diet, because ketones use a different transporter entirely and can reach the starving neurons the glucose cannot. That single disease is the clearest proof available that the brain's fuel supply is not just about how much sugar sits in your blood. It is about which door that sugar is allowed to walk through and how many doors exist. When you cut dietary sugar, you are not switching off the brain's power supply. You are changing which doors get used, and the switch has consequences most people cutting sugar have never been told to expect. Consider the actual arithmetic behind that 20% figure. Each of your roughly 86 billion neurons maintains a resting voltage across its membrane, and every signal it fires is a controlled collapse and restoration of that voltage, a cycle that runs through the same sodium-potassium pump found in every cell in your body, just packed at extraordinary density in neural tissue. Firing a single action potential and restoring the ion gradients afterward costs a fixed quantity of ATP, and a busy cortical neuron can fire dozens of times per second. Multiply that cost across 86 billion neurons running continuously, awake or asleep, and the 20% figure stops looking surprising. It starts looking like the minimum bill for keeping a network of that size electrically alive. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. Here is the detail that gets skipped in almost every conversation about sugar and the brain. Your liver manufactures glucose on its own, continuously, through a process called gluconeogenesis, building it from amino acids and glycerol, and through glycogenolysis, breaking down stored glycogen reserves. Even on a diet with 0 grams of added sugar, your blood glucose does not fall to 0. Your liver defends a blood glucose range near 70 to 100 milligrams per deciliter, whether you eat a donut or eat nothing at all, because your brain's demand for glucose is not negotiable and the liver is built to meet it, regardless of what crosses your lips. So what does cutting dietary sugar actually change, if the brain's baseline glucose supply is defended anyway? 3 things, and none of them are what most people assume. First, the insulin spike. A large intake of sucrose or high-fructose corn syrup triggers a sharp pancreatic insulin release, and insulin is not just a glucose storage signal, it also alters which amino acids compete for transport across the blood-brain barrier, a detail covered in the next chapter. Table sugar is half glucose and half fructose, and fructose is metabolized almost exclusively in the liver, not directly usable by neurons at all. Heavy fructose intake drives fat synthesis in the liver and raises triglycerides, an indirect route to brain effects through vascular health, rather than a direct fuel pathway. Third, the frequency and size of the resulting glucose swings, the sharp rise and the reactive dip that follows a large sugar load, a pattern your brain experiences as a repeated cycle of abundance followed by scarcity, several times a day, for years. Remove dietary sugar, and the liver's steady baseline supply continues exactly as before. What disappears is the spike and crash cycle riding on top of that baseline, along with the insulin signal that came with it. That insulin signal turns out to matter more than most people cutting sugar realize, because it was quietly doing a job connected to mood. There is a backup system worth naming here too, because it explains why cutting sugar rarely causes true hypoglycemia in a healthy person even during the adjustment period. If blood glucose starts to drift down, the pancreas releases glucagon, which pushes the liver to release more stored glycogen. And if the drift continues, the adrenal glands add epinephrine and cortisol into the mix, both of which raise blood glucose through separate pathways. This counter-regulatory cascade is fast, usually resolving a dip within minutes, and it runs whether or not you have eaten sugar recently. The brain's glucose floor is protected by hormonal redundancy, not by the sugar bowl on your counter, which is precisely why it can afford to keep functioning, while the slower systems, the ones covered in the next 4 chapters, take their time catching up. Richard Wertman and Judith Wertman at MIT spent decades studying a specific chain of events that starts with a carbohydrate meal and ends with a change in brain serotonin, the neurotransmitter most associated with mood regulation. The mechanism is not mystical, it is transport competition, and it runs like this. Tryptophan, the amino acid your brain uses to build serotonin, has to cross the blood-brain barrier using the same transporter that carries several other large neutral amino acids, including leucine, valine, and tyrosine. Those other amino acids circulate in your blood, bound to protein you have eaten. Tryptophan competes with all of them for the same limited number of transporter slots, and under normal conditions it tends to lose that competition, because there is simply more of the competing amino acids in circulation. A carbohydrate-rich meal changes the ratio. Insulin released in response to that meal drives the competing amino acids, leucine, valine, tyrosine, out of the blood and into muscle tissue for storage. But tryptophan is barely affected because most of it travels bound to albumin rather than floating free. The competing amino acids drop, tryptophan does not, and the ratio of tryptophan to its competitors rises. More tryptophan crosses into the brain. More serotonin gets synthesized. The Wertmans documented this pathway across multiple studies published through the 1980s, and it remains the accepted explanation for why a carbohydrate-heavy meal can produce a real, measurable lift in mood, not a placebo effect, an actual shift in brain chemistry driven by amino acid transport competition. Cut sugar and refined carbohydrates sharply, and you remove a meaningful share of the insulin spikes that were tilting this ratio in tryptophan's favor. For some people, this barely registers. For others, especially in the first weeks of a strict reduction, it shows up as an irritability or a flatness that gets blamed on willpower or blood sugar swings in a vague sense, when the more precise explanation is a transport ratio that used to get nudged towards serotonin synthesis several times a day and now does not. This is not a reason to avoid cutting sugar. It is a reason the first few weeks can feel worse before the underlying biology is finished renegotiating. Judith Wertman extended this line of research specifically into carbohydrate craving, publishing work through the 1980s and 1990s on why people describe reaching for starchy or sugary food during low moods, premenstrual symptoms, and seasonal affective patterns. Her argument was not that people lack discipline in these moments. It was that the craving itself is the body's attempt to trigger the exact insulin-driven tryptophan shift described above, a self-medicating loop running on carbohydrate rather than any pharmaceutical. Cutting sugar does not remove the underlying serotonin need. It removes the mechanism the body had been using to meet it, at least until other adjustments, covered later in this script, partially compensate. Nicole Avena at Princeton ran a series of experiments in the 2000s, giving rats intermittent access to sugar water, a schedule engineered to mimic a binge-then-abstain pattern rather than steady access. Her findings, published across several papers summarized in a widely cited 2008 review in Neuroscience and Biobehavioral Reviews, showed that sugar-binging rats developed changes in the accumbens, the brain's core reward structure. Dopamine release increased with each sugar exposure, and the animal's dopamine receptor patterns shifted in a direction similar to what shows up in studies of substances with recognized dependence potential. Then Avena's team pulled the sugar away and gave the same animals a drug called naloxone, which blocks opioid receptors. The rats showed teeth chattering, head shaking, and anxiety-like behavior, a withdrawal signature typically associated with opioid withdrawal, not food deprivation. Removing sugar alone produced milder but measurable signs of the same kind of behavioral disruption. This does not settle the human question of whether sugar is addictive, in the clinical sense that word carries for substances like nicotine or opioids, and the research community remains divided on how directly rodent binge access models translate to ordinary human sugar consumption. But the neurochemistry is not in dispute. Repeated sugar exposure changes dopamine and opioid receptor activity in ways that produce a real withdrawal-like state when the sugar is removed. This is the part almost nobody warns you about before you cut sugar. The brain fog, the irritability, the low-grade craving that shows up in the first week is not purely psychological, and it is not purely the glucose swings either. Part of it is a reward circuit that adapted to a schedule of frequent dopamine spikes and has to downshift when that schedule stops, the same category of adjustment that shows up whenever a brain recalibrates after any repeated reward exposure ends. Human data on this exact mechanism is harder to gather than rodent data, for obvious ethical and practical reasons, but a smaller body of human neuroimaging work has found overlapping patterns. Functional MRI studies looking at high-frequency sugar consumers have reported blunted dopamine receptor availability in the striatum compared to low-frequency consumers, a pattern also documented in some substance dependence research, though the causal direction, whether heavy sugar intake blunts the receptors or people with already blunted receptors seek out more sugar, remains genuinely unresolved. What is not in dispute is that the receptor pattern exists, and that it shifts again once sugar intake drops, which means part of what a person cutting sugar is living through in week 1 is a receptor system resensitizing itself, not a personal failure of resolve. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. George Cahill ran a set of human starvation studies at Harvard in the 1960s that remain some of the most cited work in metabolic physiology. His subjects, fasting under medical supervision for weeks at a time, showed the brain shifting its fuel source dramatically as the fast continued. Early on, nearly all brain fuel came from glucose. By several weeks in, ketone bodies, beta-hydroxybutyrate and acetoacetate, produced by the liver from fat breakdown, were supplying somewhere near 60 to 70% of the brain's energy needs. The brain that supposedly could only run on sugar was, in practice, running mostly on fat-derived ketones once given enough time to adapt. The word doing the real work in that last sentence is time. Ketone bodies cross the blood-brain barrier through a separate transporter, MCT1, and unlike GLUT1, MCT1 density in brain capillaries is low under normal high-carbohydrate conditions. It takes roughly 1 to 3 weeks of sustained low sugar and low carbohydrate intake for the brain to meaningfully upregulate MCT1 expression and start pulling in ketones efficiently. During that window, blood ketone levels may already be rising, but the transport infrastructure to use them hasn't caught up yet, and the result is the brain fog people report in the early days of cutting sugar hard, a mismatch between fuel availability and fuel delivery capacity, rather than a sign that something has gone wrong. Richard Veitch, who spent much of his career at the NIH studying ketone body metabolism, published work arguing that beta-hydroxybutyrate is not merely a backup fuel, but a more thermodynamically efficient one, generating more ATP per unit of oxygen consumed than glucose does. Once the transporter upregulation catches up, some researchers have proposed the brain may be running on a fuel source it burns more cleanly, though this remains an active area of study rather than a settled conclusion. Mark Mattson's research group, formerly at the National Institute on Aging, has also linked ketone body elevation and the periods of mild energetic stress that accompany it to increased brain-derived neurotrophic factor, a protein involved in forming new neural connections and supporting neuron survival. Mattson's broader body of work on intermittent fasting and caloric restriction, published across several review papers through the 2010s, proposed a concept he termed metabolic switching, the idea that the brief window of low glucose and rising ketones between meals, or during a sustained low-sugar diet, triggers a mild cellular stress response similar in category to what exercise does for muscle. That stress response activates autophagy, the clearing of damaged cellular components, and upregulates BDNF and antioxidant enzyme production. On this account, some of the perceived mental clarity people report weeks into cutting sugar is not simply the absence of glucose swings. It is the presence of a mild adaptive stress signal that a diet of frequent sugar intake, which keeps glucose and insulin persistently elevated, never allows to switch on. Glucose molecules, when chronically elevated, attach themselves to proteins in a non-enzymatic reaction called glycation, the same chemistry behind the browning of a seared steak, called the Maillard reaction in a kitchen, and advanced glycation end products, or AGEs, in a body. These modified proteins cross-link, stiffen, and resist the normal cellular machinery that would otherwise clear and replace them. In blood vessels, AGE accumulation stiffens arterial walls. In the brain, AGE accumulation has been found concentrated in the same amyloid plaques and neurofibrillary tangles associated with Alzheimer's disease. Suzanne de la Monte at Brown University published research through the mid-2000s proposing a mechanism connecting chronic high glucose and insulin exposure to a state of brain-specific insulin resistance, where neurons stop responding properly to insulin's signaling role even though blood insulin may still be present. Her group's language for this, brain insulin resistance functioning as a distinct pathology from body-wide type 2 diabetes, appeared in a 2008 paper in the Journal of Alzheimer's Disease under the phrase type 3 diabetes, a label that remains debated among researchers but has driven a meaningful share of current Alzheimer's metabolic research. Insulin in the brain is not only about glucose uptake. It plays a role in synaptic plasticity, the physical basis of learning and memory, and a neuron that has stopped listening to insulin properly may struggle with that plasticity regardless of how much glucose is technically available to it. The AGEs formed during chronic high sugar exposure do not simply sit inert once formed. They bind to a specific cell surface receptor called RAGE, the receptor for advanced glycation end products. And that binding event triggers an inflammatory signaling cascade inside the cell, independent of the physical stiffening the AGE itself causes. Chronic high sugar exposure therefore damages brain tissue through two separate channels operating at once, structural cross-linking of proteins the cell can no longer easily replace, and a receptor-driven inflammatory signal layered on top of it. Cutting sugar interrupts the second channel almost immediately, since RAGE signaling depends on ongoing AGE formation, while the first channel, the accumulated cross-linked protein already sitting in tissue, clears far more slowly through the body's existing turnover processes. Chronic high sugar intake also drives measurable neuroinflammation. Elevated glucose promotes the activation of microglia, the brain's resident immune cells, and a persistently activated microglial population releases inflammatory signaling molecules that have been linked in animal studies to impaired memory formation in the hippocampus, the brain structure most directly responsible for forming new memories. Several rodent studies feeding high-sugar diets over extended periods have reported measurably worse performance on hippocampal-dependent memory tasks compared to matched control animals on lower-sugar diets, with microglial activation proposed as one of the mediating mechanisms rather than a change in body weight alone. Cutting sugar does not instantly reverse years of AGE accumulation or fully restore insulin signaling that took decades to blunt, but it removes the ongoing glycation load and calms the inflammatory signal at its source, a different kind of benefit than the ones usually advertised, less about willpower or waistlines, and more about the literal chemistry of what your neurons are coated in. Put the last 6 chapters together, and the picture that emerges is not the one usually sold. Cutting sugar is not a switch that flips cleanly from bad to good the moment you stop eating it. Your liver's baseline glucose supply to the brain never wavers, because it was never dependent on your sugar intake in the first place. What actually changes is the insulin-driven serotonin pathway the Wortmans mapped, the dopamine and opioid receptor patterns Avena's lab measured, and the ketone transport infrastructure that takes 1 to 3 weeks to build up enough MCT1 density to matter. That window, roughly the first 1 to 3 weeks, is where nearly everyone who cuts sugar hard runs into trouble they were never warned about. Lower tryptophan transport pulling mood down slightly. A reward circuit adjusting to the absence of frequent dopamine spikes. A brain running on a glucose supply that is technically fine but lacking the extra ketone fuel it will eventually recruit, because the transporters for that fuel haven't caught up yet. None of these 3 things show up on a blood panel. All 3 are real, documented, named mechanisms, and all 3 resolve within roughly the same few weeks as the underlying transport systems adjust. On the other side of that window sits the part almost nobody frames as brain biology at all. Reduced glycation load on cortical proteins, a calmer microglial population, insulin signaling in neurons that gets a chance to recover some of its role in synaptic plasticity. Possibly, if Veitch's efficiency argument holds, a brain running a meaningful share of its energy on a fuel source that generates more usable energy per breath of oxygen than the sugar it replaced. None of this means the transition has to be abrupt or absolute to matter. The mechanisms described across this script scale with the size and speed of the reduction, not with perfection. Someone who cuts added sugar gradually over a month experiences a milder version of the tryptophan dip and the dopamine adjustment than someone who eliminates it overnight, and both eventually arrive at the same destination, a brain that has finished renegotiating its fuel contracts and quietly reaps the benefits of a lower glycation load without the sharpest edge of the adjustment period. There is no single correct speed, there is only the physiology, running on its own timeline regardless of which speed a person chooses. The instruction to cut sugar was never wrong, it simply arrived without the physiology attached, and the physiology is the part that explains why the first weeks feel the way they do, and why what comes after is worth the weeks it costs. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story. Frequent dopamine spikes. A brain running on a glucose supply that is technically fine but lacking the extra ketone fuel it will eventually recruit, because the transporters for that fuel haven't caught up yet. None of these 3 things show up on a blood panel. All 3 are real, documented, named mechanisms, and all 3 resolve within roughly the same few weeks as the underlying transport systems adjust. On the other side of that window sits the part almost nobody frames as brain biology at all. Reduced glycation load on cortical proteins, a calmer microglial population, insulin signaling in neurons that gets a chance to recover some of its role in synaptic plasticity. Possibly, if Veitch's efficiency argument holds, a brain running a meaningful share of its energy on a fuel source that generates more usable energy per breath of oxygen than the sugar it replaced. None of this means the transition has to be abrupt or absolute to matter. The mechanisms described across this script scale with the size and speed of the reduction, not with perfection. Someone who cuts added sugar gradually over a month experiences a milder version of the tryptophan dip and the dopamine adjustment than someone who eliminates it overnight, and both eventually arrive at the same destination, a brain that has finished renegotiating its fuel contracts and quietly reaps the benefits of a lower glycation load without the sharpest edge of the adjustment period. There is no single correct speed, there is only the physiology, running on its own timeline regardless of which speed a person chooses. The instruction to cut sugar was never wrong. It simply arrived without the physiology attached, and the physiology is the part that explains why the first weeks feel the way they do, and why what comes after is worth the weeks it costs. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.